Hi everyone. So today I'm going to be talking about Consul and giving you an introduction to what a service mesh is. I'm Nicole Hubbard and I'm one of the developer advocates for HashiCorp focused on Consul. So one of the questions I get asked the most from practitioners that I talk to is, what is a service mesh? The question that quickly gets asked after that is, why should I be using a service mesh? What will it do for me? So today we're going to take a minute to understand how we got to the point where we need service meshes, as well as what they can help you do, as well as do a demo of them. So let's start with our history of services. So when we started off deploying our applications, we started off with this clearly defined network. We have a firewall protecting our entire perimeter. All of the traffic comes in through that firewall, hits a load balancer, and from there it's routed to our 3 application servers. Those 3 application servers then talk to the database server. In some cases, you actually have an additional firewall between your web service and your database to help ensure that only the web servers can talk to the database. And so there's no additional ingress points to our application. There's only one way in. There's only one set of things talking to the database. It's very simple, it's very easy to understand, and very easy to secure. So when we started with this deployment approach, we were deploying monoliths. And so in this case, we have a service that's actually made up of 4 different subsystems. And so when these subsystems, like for example, subsystem A needs to talk to B, which could be potentially your ordering system needs to talk to your payment subsystem. They just are able to communicate over function calls in memory. They don't have to understand where the other service lives because they're all part of the same service. But as we've grown and we've started to break all of these systems into microservices, we now are actually deploying all of these systems independently. They're running independently, and it creates some new problems with the communication between these systems. So now, when service A wants to talk to service B, or like we mentioned earlier, or ordering system talking to the payment system, how does service A find where service B is? How do they communicate? How does that process get started? And so what happens is we typically configure an IP address or something. But then what happens when we add additional instances of B? Do we go back? Do we update the config in service A on how to talk to the payment system in this case? No, generally that's a lot of additional overhead and doesn't allow us to scale our applications. So what happens in a lot of cases is we'll add a load balancer. And this load balancer gives us a single point. We can give it a DNS name, for instance, that points to the IP for the load balancer, or we can assign it a static IP. And then we just point all of the traffic, in this case for our payment service, to that load balancer. And as our instances scale, the load balancer can send the request to the new instances. And this works, but it comes with some downsides. We're increasing the infrastructure that we have to maintain. We now also have an additional network hop in all of that traffic. So the traffic coming from our order system now has to go to the load balancer and then to our payment service, instead of talking directly to the service. And then also an increased cost in our infrastructure because now we also have to run this load balancer. And in some cases, this load balancer can be a single point of failure for us, where if that load balancer goes offline, we no longer can communicate with all of the services behind it. And so if we look again at our traditional data center, where we have this set up, and then we start looking at what a modern data center looks like, we can see that we've started to add additional things. So we've still got our traditional data center here on the left, but now we've extended this potentially into new hardware in our own data center, into a cloud, or any other systems. And so, but in our new environment, we're running Kubernetes. And we've got our own database server over there, key value servers. The database servers need to be able to communicate to one another. Our old web servers still need to be able to talk to the database. Our Kubernetes applications need to still be able to talk to the old database as well as the new database and key value store. And we start to add more and more rules that we have to define on all of our firewalls to protect our environments. And so this gets harder to maintain as we grow. and we're having to rely on networking potentially to actually go in and make those changes for us, because there's a lot of times as software engineers, we don't have access to those systems and to the ability to maintain them. And with Kubernetes, this gets even harder as you're scaling out. And so as you start to grow your infrastructure and have more and more microservices, you start to run into three main challenges. And those are how your services are going to talk to one another, how you're going to limit communication between services, and how you're going to configure the services so that they can communicate and they can be adjusted in real time on the network as changes need to happen. So let's start with service discovery and the other important piece to that, the registry of your services. And so in our case here, we've got our service A and service B, and service B is starting and it's going to register itself with the service registry. And so now the service registry knows that service B is available at these 3 IP addresses. And so when service A wants to talk to service B, service A is able to ask the registry, hey, where can I find service B? The registry then returns, hey, B, you can talk to B at 1.2.3.4. That's just one of the 3 addresses, but it's the one that was returned. So then we're able to see that service A can connect directly to service B, and there's nothing in the middle for the communication. And so that full process involves registering, discovering, and connecting. And this is one of the pieces that you get using a service registry and service discovery. And it will make up the beginning of our service mesh for us. So the next piece is service segmentation, which is how do we limit what services can communicate with one another? And so in our previous example with a monolith application, we had our load balancer coming in, we had our monolith application that received that request and then talked to different subsystems within the same application. And then those applications had to make calls back out to the database. We were able to hard code the database with a static IP. We used a firewall between the application and the database. We also had a firewall between the load balancer and internet, or our internal network that accessed our application, and the service to help protect the service. But as we've moved to microservices, where all of these services need to be able to communicate, but sometimes not always. So we have a bunch of disjointed systems that have different requirements to communicate. So as we can see, A needs to communicate with B, C and D need to both be able to communicate with one another. And then we have a case of A needs to be able to communicate with C and B needs to be able to communicate with D. But there's cases where the applications don't have to talk, like A and D have no communication requirements and B and C have no communication requirements. So we don't want to allow those services to communicate with one another. And so as you start to define these, it gets pretty easy to do with 4 microservices. But what happens when you have thousands? We work with some customers who have upwards of 4,000 microservices that they're managing intentions between and trying to limit which applications can communicate with one another. And so as you grow, you need a way to programmatically define these rather than trying to create networking rules or VLANs or ACLs or anything along those lines. And so this is where our intentions can come into help. And so the next piece is service configuration. And so when we're running our services, we need them to be able to communicate securely. And so one of the first pieces to that is configuring a certificate authority. And so this will be another one of the key pieces to our service mesh. And so what happens is we generate certificates for all of our applications that are running. These are automatically generated, they're automatically rotated, and these are the same X509 certificates that are used by websites and all traffic that's secured over the internet for web traffic. And so this allows us to start to think of our network as a zero trust network, and we're able to secure all of the communications between our applications without making changes to our application, just by leveraging our service mesh. And so these certificates allow us to both encrypt the data to secure it, as well as provide identity. Since all of the certificates are generated by us and generated by our own certificate authority, we're able to concretely say that this service, who's identifying itself with this certificate, is indeed who it says it is. And so now that we have all of these pieces, we can actually start with our service mesh. And so one of the big things with service mesh is there's two different components to it. There's the control plane and the data plane. And so when you're running your applications and your applications are communicating with one another, all of that remains in the data plane. It never goes into the control plane. Your traffic is never routed for applications into the control plane. And so these rules are defined in the control plane though. So in this case, we're using Consul for our control plane, and we're going to use Envoy as our data plane proxy to actually move all of the traffic. And all of our nodes have a Consul client running on them. And this will actually cache all of the rules for our environment so that those requests aren't having to ever leave the local machine we're running on. And as changes happen, they're pulled down. And only the instructions that are needed are actually saved per machine. So the next piece is being able to actually limit that communication between services. And so Consul does this with what are called intentions. So here you can see the first thing we're going to do is we're going to create an intention, and we're going to deny the ability for our web server to talk to anything. And so now our web server can't access any of our other services. And then the next thing we're going to do is we're going to come in and we're going to create a new rule that says our web server can talk to our database server. Now, these rules will apply no matter what server our web service is running on. We can migrate it between servers because these rules are based on the service, not the location of a running process. And so as long as our service is defined, and when we move it and we don't change the service definition, those same rules will continue to apply. So we could actually run our web service in multiple clusters that are connected together with Consul, and all of the same intentions will apply. Also, the intentions are defined with the most specific intention applying first and the least specific applying next. So in the case of the web server trying to communicate with the database, we have a specific rule that says that that's allowed, so it's allowed. And then anything else, there's no specific rules for, so it'll fall back to our web say anything rule and get denied. We can also manage these intentions in a single UI. So in one UI, we can actually come and we can actually see all of our rules on what communication is allowed. And so from here, we can create deny rules, we can create allow rules, we can even create rules that say, a default deny all so that no communication can happen within our cluster. And then we have, how do we integrate this with our application? So you're probably thinking, what do I have to change to actually be able to use this? Is this going to take a lot of development work, or is it easy? And the good news is this is very simple to add. For the most part, this doesn't really require any changes to your application directly. What happens is we will deploy a proxy that will run right next to your application, and it will handle all of this traffic for you. So you don't have to change anything in your code. The only thing that has to change is the endpoint that you talk to get to the database in this case. So instead of your web server knowing the direct path or URI to your database, instead it will talk to something on localhost and a port that the proxy is listening on, and that proxy will then pass that information wrapped in the TLS, and the intentions will apply. So in this case, we're going to deploy this into Kubernetes. And to make it easy for you, we provide a Consul Helm chart to help you get started. And one component of our Kubernetes deployment is a connect injection. Connect is what we refer to as our service mesh functionality that allows secure communication between services. And so all we have to do is add this annotation that says console.hashicorp.com/connectinject is true. And this will automatically add that sidecar proxy for us without us having to do it. And so when we deploy this, what happens is now we've got our web server running on one server with the proxy and the console client running. And then we've got our database service running somewhere else on some other server, maybe inside of Kubernetes, maybe on hardware. And then it's got its proxy server and its console client. And so when our web server needs to communicate with the database, what happens first is the web server opens that connection to its local proxy on a localhost port, and the proxy will go out and do the service discovery we talked about. And it will ask its local console client, hey, where's the database that I need to talk to? The console client is going to look at all the information it has cached, and it's going to say, hey, the database is over here. This is the address for it. And then the proxy will open a TLS handshake connection to the proxy server for the database. And then what's going to, wrong way, there we go. And then what's going to happen is the console client is going to get asked by the proxy for the database, hey, is the web service authorized to talk to me? I'm the database service, by the way. And in this case, we've created the intention so that that is allowed. And so the console client is going to respond with yes, at which point the TLS connection will be established. Had it been a service that's not authorized to talk to the database, the console client would have returned no, and the TLS connection would have been immediately terminated. So what are some of the extra benefits we can get with this? So one thing you can do is you can also configure mesh gateways. And so mesh gateways allow you to extend your service mesh across multiple clusters or into multiple environments that aren't Kubernetes clusters and are just a case of a bunch of VMs in another provider or your own on-prem data center. And the really cool advantage to mesh gateways is they can also start to solve overlapping IP problems. So in this case, our API and our web service is running in one data center and our database is in another data center. And both of these data centers are using 10.8.1.1/24 IP ranges. And so normally in the networking world, this is really hard to solve. You have to create all sorts of rules to be able to join together two networks that have the same IP space. But when we add the mesh gateways in, the mesh gateways communicate over any connection they have available to them. So it can be the public internet, it can be another VLAN, a VPN, whatever you have that's connecting these, it can use. And then your API service just talks to your local mesh gateway. It does natting effectively and forwards that request to the next mesh gateway. And then the mesh gateway there will send it over to the database, and the response is returned through the mesh gateways so that all of your overlapping IPs are handled for you. And so the mesh gateways, they're built upon Envoy still, and these handle all of that for you. And the really cool part about these is when you're deploying them, they become the only point that you have to expose to the internet to allow communications between your services across different cloud environments or data center environments. And so now instead of having to create rules in your firewall to allow all of the services to be accessed by all the other services, you only have to create a rule to expose this mesh gateway directly, and that's it. And you can even limit that rule to only allow communication from your other mesh gateways to secure it even further. And so another advantage you can get is layer 7 traffic management. And so with this, we are able to, in a standard layer 4 environment, traffic comes in for web.service.console, and it gets forwarded to our 3 instances of our web service. But with layer 7, we're able to actually change the way that traffic works. And so the first thing we can do is we can change the routing of that traffic. And then after we change the routing, we can also do traffic splitting, and then we can do custom resolution. So what does that look like? So in the case of HTTP routing, we can say if a request comes in, that's web.service.console/API. Instead of routing that to our web service, route that to our API service and strip this /API path so that it's just / for the path when it hits the API service. And so now we're going to send our API traffic to our APIs services. And then let's say we've developed our API, we've got version 1 deployed, and now we have version 2. And we want some of our traffic to go to version 2. We can now create what's referred to as a subset for V2, and we can actually send just say 80% of the traffic to V1 and 20% to V2 so that we can start testing V2. And this allows you to start doing things like canary deployments and blue-green deployments with limited rollover at the time. And then you also have custom resolution. And so we created the subset known as V2. And so custom resolution informs the routing here, how it defines what version 2 is. And so in this case, we're going to look for some metadata we configured that is meta.version equals 2. And so we define that on our service. So now let's take a look at how some of this actually works in a demo environment. So here, what we have is I've just got a really simple application we're going to deploy. It's got a dashboard so that we can hit the UI for it. And then we've got a counting service that will provide a count as to how many services have accessed it. And so to get started, what we're going to do is deploy our Helm console chart, which we've pulled down from the public HashiCorp repo that's console Helm, which is that folder we have right here. And so to do that, we just do Helm. Before we do that, let's take a look at these values though. So there's a values file, and this allows us to change the default settings. So in this case, we're changing the data center from the default to Nicole Lab. And then we're going to change our server so that we're only running one replica of this server, and the bootstrap will only expect one instance. And then we're going to enable that connect inject that I talked about earlier so that we can automatically add our sidecars proxies. So now we can do a Helm install console, and we'll give it this values file, and then we'll give it our console Helm chart. So this will go through, and this will install for us, and now we can see we are running with our cluster. So if we check out Kubernetes now, we can see that we've got our console server running, we've got our console connect inject running, and we've got our console client running as well. And so I have k alias to kube control, so this is the same as if we were to run kube control. So there's nothing fancy or special about that. So now that we've deployed that, we can take a look if we always forget the shortcut for this. New tab. All right, so now we can go, let's go ahead and create a port forward. But first, let's get our service. And so we can see we have our UI service here, and it's listening on port 80. So let's go ahead and open a port forward to this service, and it's port 80, and we'll forward it to port 8080 locally for us. Oh, no, that was backwards. I mix those up sometimes. All right, so now we can see we're forwarding localhost 8080 to our console server so that we can actually communicate with it. So if we come over here and we actually access localhost 8080, we can see we now have our console server running. We've got one service. Our data center is console lab, and we can see we've got our nodes, and we can see we don't have any intentions at this time. And so now if we come back over here, we can come over here and we can deploy let's deploy our dashboard service. So if we take a look at the dashboard, this is a very simple YAML deployment for us. So the first thing we're going to do is deploy a pod. Its name is dashboard. It's got a simple label. We're going to enable the connect inject true. And we're going to also tell the proxy that we want this service to be able to communicate with counting on port 9001. So this will open something for us on the dashboard pods on localhost 9001 that forwards to our counting service. And so we're going to run the dashboard service on 9002. And we can see that we're specifying that the counting service URL will be localhost 9001. And then we just define a service so that we can actually expose this. It's port 80 locally that goes to 9002, and it's just a very simple load balancer service. So we can apply this now. And if we look at our pods, we can see that the dashboard now is doing an init container, which we didn't specify an init container, so what could that be? And we can see now that the dashboard's running, and there's a total of 3 containers running. So what are those? So let's take a look at our dashboard pod. And we can actually see in all of this that we have a couple of different containers running, if we get all the way up here. So we can see we had an init container added. That's our console connect inject init container. So this handles setting up our sidecar proxy for us. And it's the script that runs, it gets all of this information. All of this was defined automatically just by adding that one line. Then we've got our containers. So here's our dashboard container, which is our dashboard service that we defined. And then we can see that we have a console connect envoy sidecar container running, which is running envoy for us and is our sidecar. And we can see that we're also running somewhere a console connect lifecycle sidecar. So those are now 3 containers when we only defined the one. And so now if we come back over here and look, we can see we have our dashboard service registered as well as the sidecar proxy. And so now let's go ahead and deploy our counting service, which looks very much the same. We create the service count for it. We create the pod. Since we're not accessing this directly and we're only ever going to communicate with this service through the console connect network, we don't define a load balancer or a service in Kubernetes for this. And since the counting service doesn't talk to anything, we're not defining any upstreams. We're only enabling the proxy. So we can go ahead and apply this now. And we can see here, as these start, they will register. So now we can see we have our counting sidecar proxy, and we have our counting, and we can actually see this one's not entirely online and hasn't passed all of the health checks yet. Now it has, and we can see that now we're able to use both of these services. And so if we come over here and we actually port forward, let's get that service first. So we can get our dashboard service load balancer right there, and we can port forward. Oh, need a dash. Oh, wait, that wasn't what we wanted. Since we're doing it to the service, we have to find that, and then this will be port 80, and we'll forward this to 9090. And of course I did it backwards again. All right, so now we can access 9090 locally. And we're able to see, here's our counting service running, and we've actually communicated with our backend counting service once. Now it's been communicated with 4 times, 6 times. There's health checks. This service actually runs, so those counts get increased. So that's why they increase more often. But now if we come in here and we create a new intention and we say, don't allow any services to communicate with anything by default. Let's call this just default deny, and we save it. So now we have now blocked all access between services. And if we come back over here, we can see when we refresh that now the counting service is unreachable. So we have now effectively disabled the ability for our services to communicate without specific intentions being created for them. So now if we come over here and we say, let's go ahead and allow traffic from the dashboard to the counting service, and we save it. So now we have this rule, and we come back over here and we refresh. We're able to see, now we're able to connect again, and everything is allowing communication to flow between these without any problems. And so just like that, we've been able to create firewall rules that allow this, and these apply pretty much instantly. So if we delete this intention, as quickly as I can come back, before I could even refresh it, the dashboard had already realized it lost the counting service. So these apply across your network in real time, no matter where your applications are running, and allow you to do amazing things with that. And so there we go. And so I'd like to thank you for taking the time to learn more about how Consul Service Mesh works, as well as how Service Mesh works in general. And hopefully you're able to take this and apply it to help secure communications between your applications, as well as help you do things like blue-green deployments or canary deployments. Thanks.